Hello and welcome to another video. It's a bit of a different video. Already tried recording this, but we'll try again. Essentially, today I'm going to show you guys some performance optimization and how to do that and what's important when you do some sort of optimization in your code. I'll show you some tools and I'll show it on a real example because I have code in front of me that is slow and I don't know why, and it needs to be fast, okay? And we'll actually start with step 0 of performance optimization, which is, does it need to be fast? And this is the first answer, the first question you need to ask yourself. Does it need to be fast? And which parts need to be fast? And how fast, right? Those are the questions that really matter, because if you don't know these, then you don't really have anything, like any reason to do performance optimization, because you're like, I want it to be faster. Yeah, why, right? Why does it have to be fast, and how fast does it have to be, right? I'm going to show this on, as I said, a real world example that I'm working on right now. And in the next, let's say 5 minutes, I'm going to give you an overview over what this product is and why it matters. It's open source, so I'm not pitching this to you to sell it to you. But it's just important to understand what it does in order for us to understand what the, what all the things are that I'm going to be talking about, so I don't have to keep like half-assed explaining what I'm doing. So the next, let's say 5 minutes, you can skip ahead if you don't want to hear about this. Please do skip ahead if you don't care, but I'm going to give you a quick explanation. So what we're working on is called Voltlane. You can go to voltlane.net to read all this and whatnot. I'll give you a very quick rundown. I'm basically going to give you this pitch, but in real life, or, So let's say you have a game and your game has players. Okay, so it's a multiplayer game. And so you have a server, which is the thing on the right. I'm going to put an S in it. S. And these are the clients 1, 2, 3, and so on. And so you have N clients, okay? And so your N clients all use TCP to connect to your server. Let's just pretend that's the case. And this could be a game. This could be what other examples did I have? An IoT app. It could be anything, right? So you will have to deal in your server, with N TCP connections, which means that you will have to have some sort of concurrency going on. And, I could explain why, but it's probably going to take 10 minutes. So we're not going to do that right now. But essentially, you really can't get around having N tasks of some kind running running at the same time concurrently, whether you do it asynchronously or you do it in a thread pool or dedicated threads for each client, whatever you do, you're gonna have to do threading or async, and that means you have to do concurrency and concurrent safe programming. So you probably want to do either message passing between the threads or some other sort of thing, mutexes, whatever, to sort of synchronize them. And suddenly your entire server is built around having N connections, and the entire architecture has to sort of bend over to make this possible. And that's not a bad thing necessarily, right? Because that's the whole point of the server. But I've written enough multiplayer things and then chat servers and all sorts of multi-threaded networking stuff that had to be quite fast to know that this is hard and this is not a problem that you can easily solve. Now, of course, especially if you're writing it in C or in C++, or in languages that have very poor multi-threading and safety. And sorry if you're offended, I'm a huge C++ fan, but it's just kind of horrible to do multi-threading in it. And so what Voltlane does is, instead of having these connections go straight to the server, you have a Voltlane, sort of a proxy, right? And so this Voltlane proxy is just a single binary that you just run. It's nothing fancy, right? You just fucking execute it on the same machine, most likely. And then all the connections will go to it. And it's just going to multiplex them into one big fuck off connection to the server, okay? So it basically acts as a reverse proxy, I guess, for TCP connections. It does a lot more than that, but essentially that's what it is. And it's written in Rust, so that way the performance is reasonable. And also, right, it's pretty safe. So if you have attacks on these sockets, you're not going to have to worry too much about the safety of that program, because the program is by default is memory safe, and it's multi-threading safe as well because I'm only using multi-threading safe primitives and stuff. So, or Voltlane is only using those, right? So essentially we have, for example, client 1 says something, right? So this is its message. Let's call that M1, and M1 is being sent to Voltlane, right? So Voltlane forwards that and says to the server 1 said message 1. And then the server says, oh, cool, reply. So this is this direction. And then the server can reply with, I don't know, response 1, whatever you want to do, right? It says to 1, response 1, and then of course the response 1 is being sent to the client number 1. So it's just, this is your multi-threading primitive. Your concurrency primitive is a single TCP connection between your server and Voltlane handles all the other shit. Another thing that it does is it handles reconnection. So if your clients sort of drop the network and stuff, Voltlane will buffer packets for it and not let you know about it. And then, it does, when the clients reconnect, it does some sort of validation that that is still the same person by using some asymmetric encryption to figure that out. And then it's sort of gives that client an update on what it missed and stuff like that. So there's a lot of nice options, right, that you can enable. And it's open source on GitHub. We're going to go through that in a second for this performance optimization. I go through the code, but essentially that's what it is. So this has to be stupid fast, right? Reasonably fast, let's say, because I'm only human. But essentially, because this has to be reasonably fast, if we have a performance problem, that's not so great. And because the Voltlane protocol is not super trivial, there's actually a specification here you can read if you want. It's pretty short, but meaty. Because it's actually not trivial, we have a library for the server to talk to the Voltlane, but that's actually really trivial. You don't really need to use that. But if you want to implement your own clients, which you do, if it's your app, and the clients should talk to Voltlane, then you need to use our Voltlane library. And that's a little cringe, and it's written in Rust, and that's mega cringe if you want to build your clients in C, because for whatever reason, right? So now we get to the meat of it. I'm building C bindings for my Rust code so that you can use a C program. Here's a example program, main.c. Essentially, we make a new connection. We then get a line from the user. We send it VL connection send, which is like Voltlane send. And then we receive, and then we echo that. So it's just literally I type in hello, and then the server will send me back hello, because in this example, the server over here in today's example is just a stupid echo server. So whatever you send it will send back. All right. Okay. That's all the context you need. 8 minutes. Fantastic. So that's everything you need to know. All right. So the thing is, my C library is slow, and I'll show you what I mean. And I'm very, very unsure why this is. So if I do, actually, I need to first go into the examples and run cargo run release bin echo server. So this will run the echo server, which is, as I said, just a server that sort of, echoes back. It's literally this. This is the entire code. Receives a packet and then sends it back. Very simple. And then, of course, the actual connection server, con server, also run that in release mode because those are fast. And so now the connection server, which is the Voltlane server, is now connected to the echo server, right? So they're now connected. And so now I'm gonna go, oh, sorry about that. Silly me. So now I'm gonna go into the examples and I'm gonna cargo run the test client in release mode. And what you'll see is that I can now type, I don't know, so this is now a client, right? So I can type hello and it will send me back hello. So this is the most simple TCP client server thing, except I have Voltlane in the middle, right? And you can see Voltlane's sort of keeping track of the connections and stuff like that. And now, yeah, I'm not going to show too much of that, but essentially if I spam, right, everything I say, it will say back to me. Okay? So what I can do is I can actually feed it random data. And then I don't want to see the output, but I can pipe that into PV to see how much data it's sending back. So essentially what we're doing is we're saying, instead of me typing in shit, I want to pipe in random data at like some multiple gigabytes per second. It's mega fast. And then I want to see how much data I get back, which is PV. And then I don't want to see like what the data is because it's random data, right? So if we run this, we see that we, at the moment, we're looking at about, that's actually pretty slow, probably because I'm recording. But essentially, it's now like, it should sort of go around the 20 megabytes per second mark, right? So 15 to 20, if I'm not recording, it's 20 to 22 megabytes per second of throughput, which is not horrible. I think if I run all zeros, it might be faster because I might be limited by something here. No, but you can see that the speed is sort of like that, right? But this test client is actually written in Rust, right? And I have my C bindings, which is essentially just a C library here that binds to Rust code, right? So we call C functions, but actually we call Rust code, right? And the actual code is this. And I have a few ideas of what's slow here, but this is really slow. So if I run the test client C, which is actually, which is here, which I have to, let me use it has a make file because I couldn't be bothered. It has debug symbols and it's compiled with optimizations and with link time optimization. So as optimized as you can get, we're using the release build of the library so that it's as releasey as it will be, right? And so if I now do make, actually let me do this to make sure. Yeah, no, it's correct. So now I have this test binary that I can use, and I can, again, this is written in C, but it is still the same thing, the same code running. It's just being called from this C library, from the C code, right? But if I do the same thing that I did before, right? And I do the same thing as I did before, just with this client, we see that we're now at 2 megabytes per second instead of 15 to 20. And that's odd, right? Because look, if I, like the send, right? VL connection send is literally just a wrapper. Like VL connection send is just a wrapper around send size prefix, which is the same thing that the other client is sending. Now, of course, there is a bunch of code here, but this is mostly just safety related bullshit that we don't really need. And it might be this. I don't know if I actually need this, but this is the second step of performance optimization. The first step is, of course, figuring out why does it need to be fast and how fast does it need to be. So it needs to be fast because it's a connection server. And how fast does it need to be? Well, fucking 10 times faster than this, right? Well, not 10, but 8 times faster than this. So this needs to be as fast as the other test client because it's doing the same thing and it's using the same library, right? So something's fucking pessimizing this, right? So the second question you have to ask yourself is, do I know for sure what's slow? And I can say, oh, maybe this is slow, or maybe this is slow, or maybe this Tokyo RT block on thing is slow, or maybe something else, maybe this is slow. I'm sure it is, but I don't know. Okay, so this is actually, I'm not solving this problem right now. I'm just guessing. Guessing doesn't count. If you're guessing where your performance problem is, get the fuck out. Because what you have to do is you have to profile, okay? And because we have debug symbols, as you can see, there's debug info in here. It's a release build with debug info, important, right? And what we're gonna do is we're gonna also do the same with the library. Oh, actually, no, we don't need to. And we're going to use something called callgrind. So callgrind is actually valgrind, or valgrind, whatever you want to call it, with tool callgrind. And it's essentially a correctness and all sorts of analysis tool. It can do memory analysis, memory usage analysis, and performance analysis. So there's also perf, also cool. But we're first going to start with with callgrind, because I like it. Now I have this exact thing aliased to callgrind, so that's what I'm using, but it doesn't really matter. So let's run the test client and let's just give it some data and do the exact same thing that we did before. Now, one thing you'll have to know is that Valgrind actually really slows down your program, right? So you can see that now instead of 2 point something, we have 1.4 megabytes per second of throughput. That is not great. Another thing here is that like we're doing some, like if we're calling printf, we're calling fgets. These are not very efficient functions. And so I would expect these to be the problem, but we'll see. So we'll let it run for a little bit and then we'll cancel it. And you can ignore all this like other stuff. We don't really care. And what we can do now is we can run a program called callgrind, which is a KDE profiler frontend. So, and I'll show you how to do this with perf as well. We're just going to first use callgrind because it's much cooler. It's a wonderful call graph viewer, and it's great. So, call grind out. So we just call it like this, callgrind, call grind out. And there we go. Let's just move that in. Come on. All right. Also, sorry that I'm using my mouse here. And also, fucking sorry that it's light mode, but I can't put it in dark mode right now. So you're gonna have to live with that unless I can. I cannot. Fantastic. But essentially what this is gonna tell us is what is slow. And I'm already seeing stuff that I don't really like, but we'll get there. Here's the call graph. So what we do is in main, which takes most of our time, we call VL connection send and VL connection receive. And you can see that VL connection receive takes most of the time. Interesting. We didn't know that before. That's new information, right? So that's cool. I literally didn't know that. This is the first time I'm looking at this, in case you didn't know. Which is spending 100% of its time in runtime block on, which makes sense because that's what we're calling right here. So that's like, this is the actual, I'm sorry, wrong function. This is the actual receive function that's being called inside of block on. So block on should actually be 100% of our time, more or less, right? Like, which is because it's like, yes, like most of our time. Whoops. And then it calls enter runtime. There's a core guard block on set. This is not very satisfying because now what we see is that a lot of time is sort of being spent in things that we don't really understand. Like none of this is our code, right? We don't want to see that. We do not want to see that. So now we have to think how we can profile this. So I think if I look at this library, oh, sorry. It's an archive. I don't know if this has debug symbols, but I'm guessing it does because we're looking at a bunch of this stuff. So let's first make sure that the library is actually up to date and has debug symbols. So what we're going to do is we're going to do cargo run, cargo build profile, and I should have a profile for release with debug, but I might not. So let's define it. This is exactly what I want. Thank you so much. Oh, it doesn't. Oh, inherits. Sorry. Inherits release. All right. Let's see if that works. It does. Don't worry about these. I'm just fucking around. Essentially, I want to build a release with debug version of this. And it's taking a long time because it's doing link time optimization. We essentially want to squeeze as much as we can out of Voltlane right now to sort of make sure that we don't pessimize by accidentally not turning on some sort of optimization option, right? Okay, so now if we do make, should copy that over, and it does copy that over. And so now let's try calling that again. So first let's just try this again. Okay, we did actually get a little bit of a performance boost there, but that's probably just random. So let's do callgrind again and let it run for a little bit. And this is actually really unsatisfying because if you see that your code is not the problem, then you have to think about your architecture, and that really stinks. But we'll get there. We'll get there. I'm going to optimize this, even if it takes us an hour. We'll see. Ooh. Oh. Okay. That's somehow worse. Okay, whatever. So main. Oh, there we go. Now we're back. I was gonna say, like, what the fuck is that? Okay. Fantastic. So we have current thread context park, Paul. That's not really that great. Decode, turn, wake, next expiration. We can look at the cost, the self costs. So for example, VL connection receive, why is that taking so long? We actually look at the source code as well and see like how long each line of code is taking. And we don't see anything egregious. We see this actually, which is not necessarily great. All right, what else do we got? We got, ooh. Okay, so the enter seems to be quite expensive. See how it says self-handle enter, enter guard? That's being caused, like this is causing like 2.99 of our cycle estimation time. And then this as well, which is inside of the guard. I think this is also guard related. There's more guard related code. So maybe this guard that I added actually is pessimizing our performance kind of horribly. Let's get rid of it and see if that disappears and if it still works. So what we're gonna do is we're gonna go out and cargo build, and then we're gonna go back, and then we're gonna make because if the enter is causing it, that would be quite the explanation, but we'll see. Nope, it's not causing it. That's still slow as shit, but at least it's still working. So that means that we can probably get rid of those enter calls. Because I only added them in an earlier debugging session, but maybe they really are completely irrelevant. I don't know. I really don't know. I'm gonna try one more time here with cache grind and call grind, and if that doesn't work, we'll switch to a different tool because there are other tools I'm gonna show you. All right. Again, connection receive taking the most time. And again, let's look at the source code. Let's see what's taking a long time. Okay, borrow, yeah, fair enough. Again, handle enter, but it's less time. So I guess we were calling enter twice, probably. This is still costing us a lot. And this seems to be inlined into this line 416. Oh, this isn't real. Yeah, okay. Very interesting that it's being inlined like that, and then we get such horrible performance. Sorry, it's quite late here. Okay, so for this sort of thing where we're really looking for, park. Okay. For this sort of thing where we're really just looking for like what's the sort of the smallest piece that we can adjust that will fix this? This sort of thing is actually pretty useless because we're still looking for like what is the actual like what's the problem, right? So what we can use for that is hotspot, and so hotspot is a profiler front end for perf. Again, Linux only, but it's pretty great. So what we're going to do is we're going to run hotspot, and we're going to put it over here, and we're going to record some data by running the not the connection server this time. Pretty good guess though. No, the Voltlane. Fuck, where is it? Examples, test client C, bin test client C. There we go. And that's pretty much all I want. I think I'm good with everything else. We're probably fine. We want dwarf. The rest is good. Don't care. So we can start recording that. And actually, we can't record that. Let's attach to a process instead. Because otherwise we can't do this piping shit that we're doing. So let's run it and let's look for it. There it is. Start recording that. And as you will see, this actually doesn't slow down your application because this is a very different way of profiling. But essentially what we're going to do is we're just going to let this run for a little bit and then I'll come back to you. All right, it's been a minute. Let's stop the recording. And that doesn't look like it's a lot of data. Let's see if we got any results. We did not get any results. Okay, it didn't really work. Let's do it differently then. I'll do it myself because sometimes hotspot is just a little retarded. No offense, but like random PV deflow. Oh, that's not working. What's going on? Why is it not doing deflow things correctly? I mean, it doesn't really matter. We can just do it. Deflow to deflow. Just don't give me any output. Thank you. Let it run for a bit and then we'll kill it again. That was a waste of time a little bit, but it's fine. It is fine. Oh, you can see all my specs here. Fantastic. That's probably plenty because this is a high frequency, so we should be fine. Now let's open the perf data, which is not, that's not the right one. There it is, perf data, 1.3 gigabytes of data. Be careful when you run stuff like this, it's a little rough. Okay. All right. So we see that there's one CPU being used, which is accurate. What else we got? We got our flame graph, which is beautiful because it finally tells us what we want to know. And we can also turn it into a bottom-up view, which tells us the most expensive single things that are going on. So for example, we see that 5% of our aggregated costs are printf, which is not only ridiculous, but it's also like, wow, you know, fantastic. And what else do we got? So printf is actually, well, it's actually 17%. Never mind, 17% of our time is being spent on printf, and 6% is being spent in fgets. 5% or 6% is being spent in connection new, which makes sense because connection new is pretty expensive. Because creating a connection actually creates an asymmetric key pair, so that you know, but you only do that once, so it doesn't really matter. And then this seems to be pretty expensive too. This is send and this is receive. So these are the functions we thought were very expensive, but they're actually not. Enter runtime, block on, core guard enter. These seem pretty fucking expensive. Now, I don't think we can get rid of these without getting rid of async entirely. or without, writing our own scheduler, which is not a biggie. We could do that, but yeah, we'll see. And so this is a lot of time spent, but honestly, I'm not super concerned. Let's first tackle these two. So in the flame graph, we see that printf is taking a lot of time. So let's get rid of it. And what can we do instead of printf? So printf is just being abused here to print. So what we can actually do is we can use write, which is fantastic. Or we could use fwrite. No, let's use write. Let's use write. So fwrite, no, write. What's the signature? Why does that show me? File descriptor buffer byte. Okay, fantastic. Then we'll use fwrite. Standard buffer, which is message data and message size. That should already be much quicker. Let's see if that's the case. What do we want to do? Bin test client C random pv null. And fwrite's not like that. Oh, right, it expects another argument. Ignore that. It's a 1. And of course it's the wrong way around. So it's actually data. See, this is when I don't got the documentation for whatever reason. There we go. Okay, 3 megabytes, that's a bit better. And instead of fgets, we'll do fread. And instead of guessing, I'm gonna just do man3 fread. And we'll just look it up, which takes a pointer, size, and stream. Okay, so pointer will be buff, 1 size of buff, standard in, and then buff and is 0. Instead of string length, we'll use n. We don't actually need the buff thing. Okay. And then if this can return a 0, right? So if this is 0, we will actually just break. All right, let's see if that works. No, it does not. Res is undeclared. Yeah, I know. Don't know why it's all erroring out. Oh, that was it. There's no way. There's no fucking way. Okay. So fgets was the problem. Why? Wait, why? Does it still work? This is the second test of performance optimization. Oh, no, it doesn't. Oh, I see what we're doing. That makes a lot of sense, actually. We can remove the perf data now, by the way. It's 1.3 gigs that I get for free now. Let me just quickly update my IDE here. Okay. Interesting. So fgets was the solution. And I think that's because getting rid of fgets was the solution. And I think that's because fgets will actually check for the new line character. And that's a little, or will it? I don't know. That's a little strange. What does fread do? It just reads until, let's actually look at, why am I speculating? So now we do actually need to pass it 1024 bytes of stuff before it sends it, which is of course much faster. If that was the solution, then actually my previous thing wasn't so bad, because I just want to know that this isn't slow, right? As long as this is the slow part, I don't really care, because it's the library that's not slow, and that's what matters. Right. Right, okay. So it is not, okay, so yeah, it waits for the render file. So what I would have to do is I would have to do hello and then press Control D. Test. Yeah, right. So if I type something like hello world, nothing happens. If I press Control D to terminate, sort of, I get it. And if I press Control D again, it sort of kills it. That's very interesting. So I guess our performance problem was really just fgets instead of fread. But maybe sometimes I want to be doing fgets, like typing Control D is kind of a pain. So this is like, now I've improved the performance back to where it should be, but I've actually changed the behavior of the program, which is not correct at all. So what I actually really want to do is I want to do is the TTY, and I probably want to do that beforehand, right? So because I still want to yeah, uni standard. And I know that this is no longer portable C code, but portable C code is like a fucking not happening, is basically what that is. So if standard in is a TTY, which means that we're like interacting with it, then we want to use fgets, of course. So if TTY, so we will have int n, and we'll have sharp no, I can't call it buff. Message. No, we can't call it message. What the fuck? What was it called before? It was called something funny. It was called something funny. Res. Why not? Yeah. Okay. And so in the TTY case, we want to do what we did before. And in the other case, we want to do this. And I'm actually brutally ignoring my code style here. Hold up. Gotta be pretty. All right. Okay, so that's, oh god, I'm butchering it. What's this IDE doing? All right, and then we want the fgets, this thing, we want that over here. All right, so if it's a TTY, we do fgets, which then means res is res. Well, actually, this should be called something else. I don't really care. And n is string length of res. I mean, it makes sense that when we were doing string length, the throughput was much slow, like much less, because you can actually use string length on a random stream of data, so that was also a problem. But whatever. Res is buff and n is, well, red. N is how many bytes for that. And now it should work for both cases. Like, no, it does not. It wants standard in file now. Okay, so now if I do this case again, hello world. Okay, that still works fine. And then also if I do this case, it should now still do 20 megabytes per second, and it does. Yippee, we've solved it. So those are the two tools that I would recommend: perf, hotspot, and callgrind and kcachegrind. So those are the sort of four tools, I guess, that I would recommend. Another thing that's really good is vtune. Intel vtune is a little bit of a fucking pain. And you know, yeah. But if you do use it, you'll be very happy, because it has options to figure out specific sort of for specific use cases. So if you do a lot of high performance computing optimization work, vTune will actually look for specific things that you would care about, like, I don't know, cache utilization stuff. It'll do a lot of that. And it's a pretty web UI, and you can run it in a Docker container. So essentially, you can spin up a Docker container, slap your executable in there, run it, and then you don't have to install all the vTune one API stupid shit that Intel wants you to do, which is great. So it's official from Intel. They have a Docker container called vTune Profiler or something. Yeah, so those are the tools I would recommend. And the most important thing is not to assume anything. Of course, I assumed correctly that fgets is a problem. But we also found other problems, like, for example, that printf was taking an unreasonable amount of time. Why didn't strlen show up? Why didn't fgets show up bigger in the profile? It's probably because it wasn't actually taking that much time. It was just like not that much computing. It was mostly probably just doing a stupid sort of implementation. Like fgets might just be implemented in a stupid way where like it won't show up in the profiler, but it does take a lot of time. I don't know. That's a sort of, or like it reduces your throughput because your strlen, so it wasn't slow, but our strlen was stopping on the first null byte, which kept being less than the full kilobyte of data. So we actually only sent like a few bytes when we had a kilobyte of data. So we were actually not performing correctly, something like that. I don't know, but we solved it. So that's the important part. If you enjoyed this, make sure that you subscribe and leave a comment and join the Discord and send me a bunch of money. All of it, if you could. Millionaire by the end of this month, please. And have a wonderful day.